maybe. All right, so we have our bridge. We've got 41 volts across the whole thing at our supply. R1 is 2 kiloohms. R2 is 6.2K. R3 is 1.8K. R4 is 3K. And R5 is 5.1K. Which resistor do we want to pull first? R1. And that's a perfectly acceptable answer to continue to do. If you want to change it up, you can. You don't always have to do R1. So, we're going to pull R1 completely out of the circuit. Leave everything else connected. We now have points A and B where it came out of. Now we're going to Thevenize this circuit from those 2 points. So step 1 is completed. We remove the load. Step 2 is we solve for either V Thevenin or R Thevenin. Again, does not matter which order we do it in. How do we go about solving for which one? Which one do we want to solve for first? Voltage, okay? So the voltage from A to B is going to be what? How do we find it? Yep, we're going to make a loop. So we're going to go from A to B. We're going to be adding both of those. Well, that's for the final when we're measuring the voltage of this guy. This doesn't come into play until at the very end when we're done solving. Yep, we're going to add them together. Because measuring this voltage this direction is only when we have R1 in play. We've taken R1 out, so that goes away. So our circuit looks like this. So all we're going to have is positive to negative, positive to negative, positive to negative, positive to negative. Yep, we're still going to be using voltage divider. So, going through to solve for our V Thevenin. The voltage Thevenin is going to be the voltage of R2 plus the voltage of R3, which is where we got to get to. So the first step is we want to find out what is the voltage drop across R2. So VR2 is equal to R2 divided by R2 plus the resistance of our parallel branch multiplied by our voltage total. Nope, because these guys are in parallel with him. Yep, so we can't just do that. So we'll have to break this down one farther step. So the R parallel total is equal to R3 plus R5 parallel with R4. Because again, this guy's going to break down to where we have this. So we have R2, R4, R3, and R5. Does everybody see that, or are we still struggling with those?
So could you walk me through how you made that little,
redraw? Yeah, redraw. Okay, so all I'm doing is I'm just trying to kind of streamline everything, make everything in a vertical position so we can see what's in series, what's in parallel. So these points are just contact points because they're not connected to anything else. Those are just opens. Okay. So the first thing I'm looking at is when I come across my for my power supply, what am I connected to? R2. So I start with here with R2 is connected to the positive of my power supply. Then, what's connected across from the backside of R2? R4 and R3. So I know that at this point, this is what I have. Right? So then I got to look, what is R3 connected to? It's connected to R5. And then, what is R5 connected to? The power source and R4. And there's one connection between R5 and the power source, and one connection between R4 and the power source. So that's where you have the one connection going in. Does that make more sense?
No, basically it's the same for all the questions, right?
Yeah. If you take out R1, you're going to have the same configuration. If you take out R5, it's going to shift a little bit, because then you'd have R1 in parallel with R2, but then you'd have 3 in series with 4. Yeah, it's still going to be the same similar shape. So now we're going to solve for the parallel total. So we have R3, which is 1.8K, added to R5, which is 5.1K. That's going to be in parallel with the 3K. So we're going to have 6.9K in parallel with 3K. We're going to see somewhere in the realm of 2K. 2.091? And again, we're just going to add those together. So the 1.8K and the 5.1K is going to become 6.9. We take that in parallel with the 3K. So you do the product over the sum. Or you take the reciprocals of everything and add them together, and then take the reciprocal of that. That gives us the 2.091 kiloohms for the parallel. Now that we have that, we can plug that back up into this value over here. Really? So, coming back into here, we have 6.2K divided by the 6.2K plus the 2.091. And then that's multiplied by our, 41. So then the voltage across R2 is what?
I got 30.66.
Okay. That's just the voltage across R2. Because I remember our V Thevenin is VR2 plus VR3. So that's just the first part of solving for V Thevenin. Before, when we were doing these, it's because the other problem that we had, and I can go up and show you this real quick, is all we had was those 3 resistors. So when we took that one out, the only values that were there was A and B, or was R2 between those guys. With this one, we've got R2 and R3. Okay, so the next step is we need to find our VR3 value in this new circuit. So VR3 is, if we look back at this, guys, remember we have 30.66 volts here. We started with 41. This all reduces down to the single parallel resistance here that we solved for earlier. Yes?
So, oh, there it is. I didn't see that the screen kind of cut off the 41, so I was kind of confused.
Oh. We good now? Okay, So now we need to find out how much voltage is going to be dropped from here to here across that parallel network. Because that's all going to reduce down when we solved here, we're going to take the 41 and subtract out the 30.66. Because those two are in series at that point, and we can just add and subtract voltages like that. So we end up with, how much? Right. Yeah. So this is the parallel voltage, is 10.34. Now, we don't care what the voltage is across this guy. We don't care what the voltage is across this one. We just want to solve for this last remaining part of it. So we're not solving for the whole circuit, just for the bits and pieces we need to be able to solve and work backwards. We don't care what those are at this point. So we're going to take, because both of these resistors have access to all this voltage, they're going to split it up between R3 and R5. That 10 volts is going to be split up. So again, we're going to do our voltage divider. We take the voltage of R3 to be resistance 3 divided by R3 plus R5, because that's all we have in this little network right here. So think of these as we're zooming into this guy, each individual component, what's going on at that point in time. So here to here, we have 10.34 volts only between those two resistors. Yes. So this is the voltage, essentially, of our parallel total. Labels are going to become very important how we're labeling these guys.
So then do we add that back up to the voltage we have for R2?
Yes, we will.
So which voltage is the 10.34 volts?
The 10.34 volts is the voltage that's going to be dropped across this parallel network. So that's the voltage being dropped across R4, and then it's the combined voltage between 3 and 5. Because 3 and 5, that's the only voltage they have access to. So now we take, what we got, 1.8. So where we were at right here with this value, we take the 1.8K divided by 1.8K plus 5.1K. And we multiply that value by the 10.34. What does that value come out to be? Which is what we'd expect. We've got roughly 2K out of 6K. We're only going to be seeing about 20% of that total voltage. It all comes down to portions of portions of portions. That's what we're solving for. So since we're still in our Thevenin, our Thevenin solving here, so V Thevenin is going to be equal to VR2 plus VR3, which is the formula we created earlier. So we have V Thevenin is equal to the 2.697 volts plus the 30.66 volts. And that gives us how much? 33.357. Okay. There is the first part of Thevenin. So it does take a little bit, but really we're just stepping through this. Yes. For these ones, I think it's an hour. Yeah, but that's the thing too, is like I'm explaining every little step too. So my goal is to at least get through one of these explaining to everybody in the time allotted for the quiz. And I'm a little long, but there's a lot of pauses and breaks and questions and BS and all sorts of stuff. So, do what? So we got the 33.357 volts. Now we need to solve for the R Thevenin. So again, we come back to our main circuit. We still have our load removed. We've now found that. So now we're going to short out the supply and measure what voltage or what resistance we're going to get between these 2 points. So this is where we're also going to redraw the circuit. I'll draw it over here on the sideboard and then I'll put it up so we're not making ourselves dizzy. So we're going to start with point A. Point A is connected up to what? We got R2. We got R4. And what else is it connected to? R5. So we have, so A is connected, we have this connection, we have this connection, and we have that connection taken care of. So now we need to look at what's on the other side of R5. R3? What's on the other side of R3? R2 and R4? So let's take a second before we get to R3 because there's lots of connections there. What do we have connecting to R2? R3, so that's where we would make this connection here. And R4. Then the other side of R3 is connected to R5. So then that takes care of all the other connections. And the reason I stopped is because R5 is connected to point B, and point B we wanted to do later after we get everything else connected up. That way we're only moving from one point to the other point instead of jumping back and forth. So, I'll move this over to the other board. For R Thevenin, we have point A connected to R2, R4, and R5. R2 and R4 are connected to one side of R3. R5 is connected to the other side of R3 as well as point B. So the Thevenin resistance now is equal to R2 parallel with R4 series with R3 parallel with R5. When I'm writing down problems like this, I will switch back and forth with these brackets just to kind of keep myself in order of what is grouped together and what's not. Because the parenthesis can only be grouped with another parenthesis. A bracket can only be combined with another bracket. That's going to come in handy when you guys get into third semester. The programs that you're using to program do not really care what bracket you use. only that things are included in the same style of bracket. Some of the programs it does matter, but generally if you use brackets like this, you can put the the curved ones, then you can put the square ones, then you can put the squiggly ones. Some things they'll mean different things, but when you're doing that, that just helps me keep straight of what's what. Do I have the right number of parentheses? Because that can be the other thing that fouls you up with the calculator.
Does that matter on the calculator if you use the bracket or not?
No, most of the time they don't have them. They just have one set. Yep. Yours does? Nice. What? Yeah, some calculators do have them, but that's all they're there for. Is literally is just extra to organize everything for you.
So then in the coming semesters, what kind of programming will you learn?
You guys are going to learn Visual Basic is the core one, but you'll also, depending on the projects you're using, you could be using any of the C's, C++, C, C Sharp, various forms of Basic. So you got Visual Basic as one flavor of it. Then there's regular Basic. There's Stamp. You could even get into Python. Not yet.
Yeah, I didn't hear the question, so everything you said was
Programming languages that we use in the robotics program. You'll also get into assembly layer and machine code. So you'll actually be programming ones and zeros into machines, into a computer system. You'll be addressing, huh? Yeah, a bunch of zeros and ones. There is some math involved because you have to get things programmed into the correct lines, but it's a lot of fun. They have these little trainers. They should still have these little trainers that like are little mini computers, and you literally punch in the hexadecimal version of binary into the lines and build up your program. 5th semester. Yep. Third is where you start programming. 5th is where you get into the advanced hardcore stuff. 4th semester is RF. That's a whole nother topic that lives in its own dimension. Next semester. Yep. Second half of second semester is digital. Yep, we're trying to find our Theven. Squirrel. Okay, so our Thevenin. So let's start putting in these values. So we've got R2. Let's see, so we got R1 is 2K, R2 is 6.2K, R3 is 1.8, R4 is 3, and R5 is 5.1K. So here, we're going to have R2 in parallel with R4. So we have a 6.2K in parallel with a 3K. We're going to add that to a 1.8K. This value is then going to be in parallel with a 5.1K. So just breaking up the formula. So if we wanted to put this whole thing, that's not going to be fun to put it all into one formula. Yes?
For the V-Thevenin, can we just gone around to like the voltage supply and then back up through our side?
Yes?
Okay.
Yes, we could have. But you still would have had to done the same amount.
Yeah.
So we have the 6.2K and the 3K. What does that give us? Okay. Then we're going to add the 1.8K into that. So we get the 2.822K. Then we're going to put that in parallel with the 5.1K. Also, just so you guys know, what I'm doing here is kind of a ladder logic. I'm just taking bits and pieces and bringing everything down as I need them. Yeah, 3.8. So we got 3.822K in parallel with 5.1K. That's our R Thevenin value. Yep. So we'll come back up here. So we got the 2.185. And now we'll come back to the 1. So we plug R1 back in here, which is 1K. And now we need to solve 2K, sorry. The 10.34 volts. Oh, this guy right here. That was just the voltage across this parallel network while we were solving in Thevenin. Yeah, so after that's the only place we need that voltage. And then we're going to take a partial amount of that voltage here and we're going to add it back to R2. So it's a value we have to solve for, but then we don't use after that point. So now we need to solve for voltage and current of R1. Easiest thing to do is just use voltage divider. So VR1 actual is equal to 2K over 4.185K, and that's multiplied times the 33.357. So the VR1 actual and the current of R1 is you take that voltage divided by the 2K. $971. I just wanted to make sure I didn't flip the 9 and the 7. 7.791. Okay. Like I said, I don't know why, but I struggle with writing those numbers down. For some reason, I'm either flipping them and I'm always second guessing myself on those. We calculated it from the voltage divided by its resistance value. Ohm's law at that point. Okay, so we end up with VR1 is equal to 15.943 volts. IR1 is equal to 7.971 milliamps. Now, we're done with Thevenin. We come back to our main circuit. We add R1 back, and we put in the voltage. So 15.943 volts at 7.971 milliamps. Now we can go through and solve this guy. So our first Kirchhoff loop, we're going to come up, we're going to go down, through here, and back up. So if we have 15.943 volts here, how much do we have across R5? Correct. 25 volt. How much? 0.66 volts. Okay, how much current do we have going through R5? .915 milliamps. And we know we're going to have current that's going to be charged in this polarity. So current flowing from negative to positive is how we're going to look at this guy. So if we have 4.9115 milliamps coming up into this guy, into this node here, we have 7.971 milliamps coming into there. How much current do we have to have in R3? And is it coming in or going out? It's coming in, which means we're going to have a polarity based like this. And how much current do we have coming in? 3.057 milliamps. Yep, because of how we're measuring. Because the current's coming in, and we're using electron current flow. So now we have our 7.97 milliamps here. We've got 3 here. What's the voltage across R3? We get 5.503 volts. So now we can go through any of our loops. We can either come down through R1, across R3, across R4, or we can come down and around. We'll just come across this way. So we have 41 here. We lose 15 here. We lose 5.5 there. What do we have left across this one? Yep. 19.554 volts there. And then the last one, we're going to come across and down because we have one more value here. We have 41 volts total. We're dropping 19.554 volts there. So how much are we having to drop across R2? How much? 0.446. Now, if we were to double check it, we could come around. We have a plus 21.446, a minus 5.503, and a plus 25.066. Gets us right back to our 41 volts. Okay. That's solving bridge circuits using Thevenin. There's a lot going on. So what we're going to talk about tomorrow is we're going to go through another current meter that offers us more protection when we are switching ranges. Because before, anytime we would switch the range, we're disconnecting the circuit, plug it in. So that's if we're in a 2 milliamp range and we suddenly start throwing 15 milliamps through it, we don't have our shunt resistor in place. So we could damage that meter just by switching our ranges. So one of the things we're going to do is we're going to build a universal shunt meter that has built-in protection on how to keep your meter from overloading while we're switching ranges. Plus, it's another good example of how to solve and analyze series and parallel circuits. So tomorrow, that's pretty much what we're going to be doing is universal shunt meter, probably for most of both hours. And then Friday, we'll cover the simultaneous equations and graphing portion of things. Any questions before we turn you loose for today? Okay, have fun, be safe, have a good night. We'll see you guys in lab tomorrow.